So hey guys, welcome to the channel CodeChef. If you want to learn competitive programming and get a good hold on data structures and algorithm, this is the correct platform for you. Every week there are several videos which will enhance your skills in DSA and several editorial videos for the CodeChef contest. So if you are new to the channel, then do subscribe to the channel and turn on the bell notification. Myself Chirayu Jain, I am a CodeChef educator, and in this video we are going to discuss about the theoretical aspects of the Bellman Ford algorithm, which comes under the series of shortest path algorithms. Okay guys, so now let's start a discussion on the Bellman Ford algorithm, right? So let's start with the aim. What is the aim of this algorithm, right? So the aim of this algorithm is similar that we have seen in the Dijkstra's. So if you have not watched the Dijkstra's algorithm, you can watch that algorithm as well. It will give you much more insights, right? And the link to that particular algorithm is in the description, right? So the aim is same. We need to find the shortest path from source vertex to another vertices that we have, right? In a graph, in the weighted graph, we need to find what is the shortest path, right, according to the sum of the weights that we have in that path, and from any source vertex to another vertices that we have in that graph, inside a weighted graph basically. So the aim is same, but why do we require the Bellman Ford algorithm, right? So the requirement for the Bellman Ford algorithm is that this algorithm is helpful when we have a negative weighted edge. So whenever in a graph we have an edge with a negative symbol or a negative weight, in that particular case Bellman Ford algorithm works, but in that particular case Dijkstra is not working, right? Because the reason is quite simple, right? If you take the negative weight, right, and if you want to find the minimum again and again, it will decrease, right? It will decrease, and hence you will be ending up into an infinite loop, right? That's why Dijkstra's algorithm does not work for that negative weight portion, but Bellman Ford does, right? We'll discuss the steps of this algorithm, but once we'll get the basic overview of this algorithm, right? So the use case is quite simple. It will work in the negative weighted edge if there is a negative weighted edge in the graph, but there are some limitations also inside the Bellman Ford, which is already solved by Bellman Ford, right? Limitations to Bellman Ford which is easily be able to detect by the Bellman Ford algorithm. Let's see what is that particular case. It won't work for a cycle with a negative weight. So if there is a cycle in the directed graph, weighted directed graph, if there is a cycle, then and that particular cycle also has a negative weight, right? Negative weighted edge, then it won't work for that, right? It will reduce to the maximum extent possible. It will again reduce to a negative value. It will again reduce to a negative value which is lesser than the previous value, right? So it won't work in that particular case, right? But it will detect that whether it consists of a cycle or not. It will detect you, right? So let us say that if you have a path like this, 1 2 3, right? This is a cycle that we have, right? Let's say we have 2, we have -3, we have -4, right? So if you start from here and if you run through it, right, you will get 2 minus 3, that is -1, -4, that is -5, right? -5. If you again go through it, right, +2, that is -3, -3 and -4, right? It is some again negative value which is on the negative side and which will be less than this particular value, and if you again go to that particular cycle, it will automatically again give you a number which is lesser than the previous one and negative, and to the more negative extent, right? So again and again it will give you a less value and you will be ending up into that infinite loop, right? So this is one case where this algorithm won't work, but it will be easily able to detect. We'll be easily able to detect whether it consists of a cycle which is having a negative weight, and it will end up to an infinite loop. So we can detect that part as well here in the Bellman Ford algorithm, right? So here are some basic things for Bellman Ford algorithm. Now let's see what is this algorithm, and let's try to understand this algorithm with the help of an example. Okay guys, so now let us try to understand the steps of the Bellman Ford algorithm, right? So this is, I have taken a directed weighted graph, and now we are going to find the minimum weighted path from the source vertex to the destination vertices that we have inside this graph, right? So the shortest path that we are going to look at from the vertex, that is the source vertex, will be, let us take this as a source vertex, right? And starting from this vertex we need to find the minimum weighted path, right? So here you can see in this graph, right, we have the negative weighted edges as well, right? We need to consider that part as well. And the thing that is, if a cycle is formulated with some negative weight, then ultimately it should be able to detect it, and then our algorithm won't work for it, right? So now let us start with the understanding of this algorithm, right? So initially we have been provided with the weights and the edges. So this is the starting vertex, ending vertex, and the corresponding weight. The vertices or the edges, we can say more precisely, are in any order, right? They need not to be in increasing or decreasing, they can be present in the any order, right? So we have decided the source vertex. Now the thing that we are going to do to formulate our algorithm is known as relaxation, right? We need to perform n-1 relaxations. So what is this relaxation is, we'll understand that in detail, and why we are doing n-1 relaxation, this is also we are going to understand, where n denotes the number of vertices that we have. So here, if what vertices we have, that is 6 vertices we have. So how many relaxations we need to do? 5 relaxations we need to do, right? So what is relaxation, right? So let us try to understand with this help of an example, or the step number 1 we can say. So this is the relaxation ones that we are going to do. This is the relaxation one that we are going to do. So relaxation says that starting vertex, let us say starting vertex I, starting vertex U, plus the corresponding weight associated with it must be less than the ending vertex, that is V weight, right? This is what a relaxation is. The weight corresponding to the starting vertex plus the weight between the edge of the starting and the ending vertex should be less than the ending vertex weight, right? So initially what we will do is, we will try to initialize all the weights corresponding to each and every vertex with infinity, right? So we'll initialize everything with infinity except the weight for the source node. This is also we have done in the Dijkstra, right? So we have initialized everything with infinity except the source node. Now we are going to follow this condition, right? If this condition holds true, then we are going to update the weight of the ending vertex. So what we will do, we will be going to update the weight of the ending vertex. Ending vertex V should be equal to starting vertex, I am mentioning it in the small u, plus the weight, right? So this is what we are going to update that ending vertex weight, right? So let's see how we can do this. Let's start with the first set of edge, right? That is 2 and 3. So what is the weight of starting vertex? That is 2. This is the starting vertex, right? So initially the weight of 2 is infinity. Infinity plus 4 is less than the weight of 3. What is the weight of 3 that we have? That is also infinity, right? So we are adding something to infinity, right? So that means a bigger value, right? So that is not true, so we will not update it. Starting from 1 and 2. So weight of 1, what is weight of 1 as of now? That is infinity, plus minus 3, right? Plus minus 3 is less than 2, right? So decreasing the weight of infinity does not mean that we are updating some value. Again, it will form to some infinite value only. If we look at this, right, if we subtract something onto this and we compare it with infinity, then by what value we should update it, right? The value which we should update is in starting vertex plus weight. That means infinity minus some value that will again result into some infinite value, right? So we are not updating anything with respect to this, right? So that is also remains stagnant, right? That is also remaining stagnant. That is also some maximum value, right? Let us start from this 0, 1 and 4, right? So if we start with 0 and 1, so what is the weight corresponding to this vertex 0, right? So the weight corresponding to this vertex 0 is 0 plus 4, right? Plus 4, that's what we need to do, right? Plus weight associated with that is it less than the weight on vertex 1? Yeah, it is infinity, right? On vertex 1 there is infinity, so yeah, 0 plus 4 is less than infinity, obviously. So what will be the updation at the ending vertex? That means at vertex 1 we'll update with the weight that we have found, that is 0 plus 4. So at vertex 1 we'll update the weight. So what will be the new weight now? The new weight will be 4. The new weight will be 4, right? So this part of the relaxation is done, right? Now we'll do similar thing with 5 and 4. So 5 and 4, 5 is infinity, right? Plus 1 is less than infinity. No, that is not, updation will not do. 4 and 3, right? 4 and 3, infinity minus 2 is less than, no, right? So this is the same process, we'll do it again and again, right? 4 and 2, right? 4 and 2, infinity plus 7, right, is less than infinity, no, right? 1 and 5, right? If you look at this carefully, 1 is already updated, right? So 4 plus the weight corresponding with this edge, that is minus 5. 4 minus 5, is it less than infinity? Yes, minus 1 is less than infinity. So we'll update what part? We'll update this 5. So weight at 5 will be now minus 1. Weight at 5 will be now minus 1. So this is the single iteration of the relaxation that we have done, right? How many times we need to do? We need to do n minus 1 times, right? So this is the relaxation 1. Let's proceed with the relaxation 2 now. So now what values do we have? We have 0 for this, right? So let's make it a different color. We have 0 for this, we have 4 for this, we have infinite, 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 and minus 1 for it, right? Now let us start with the relaxation again. Okay, so how we can do the relaxation is the same process. We'll start with the beginning of this edge, 2, 3, right? Infinite plus 4 is less than 3, no, we'll not update it. 1 and minus 1 and 2, 1, we have the weight 4, 4 plus minus 3, that is 1. Is 1 less than the weight of 2, that is infinite, right? So yes, it is less than, so we'll update it, that will be 4 minus 3, that will be equal to 1. We have updated it, right? So according to this formula, we are trying to update it. Now 0 and 1, 0 and 1 is the same thing, right? What is the weight of 0? That is 0 plus 4 is equal to the weight of 1, that is 4, right? So we have already taken this in the previous relaxation, right? Now let's look at this 5 and 4, 5 and 4. So 5 is updated in the previous relaxation, that is minus 1. So minus 1 plus 1, minus 1 plus 1 is 0, right? Is it less than the weight of 4? Yes. So we'll update the weight of 4 as 0, right? This also updated. 4 and 3. So 4 is updated as just now, right? So we can update 3 as well. So 0 minus 2, that is equal to minus 2, 0 minus 2. So minus 2 will be the weight of 3, right? Because now at present is it infinite, so minus 2 will be updated, right? So it will update the infinite weight with minus 2. Now let us look at 4 and 2, right? 4 and 2 we'll look at. So what is the weight of 4? That is 0 plus the weight associated with this edge is 7. So 0 plus 7, is it less than the weight of 2? No, the weight of 2 is already less, that is 1, right? So we'll not update it. 1 and 5, right? 1 and 5. So 4, right? 4 and minus 5, that is minus 1. So it is already minus 1, right? It is already updated, right? So in this relaxation, in the relaxation 2, we have updated 3 vertices, that is with 1, minus 2 and 0. We'll copy the same thing in the next part of the relaxation. Now if you see here, 0, 4, 1, minus 2, 0 and minus 1 are now the things for this relaxation, and we can see whether we can more updated or not, right? So if we start with this relaxation, right, 2 and 3, so moving from 2 to 3, so what is the weight at 2? 1, right? And what is the weight corresponding with the edge? That is 4, right? So 1 plus 4, that is equal to 5. So at weight of 3, we have already minus 2, which is a better option, so we'll not update it. 1 and 2, right? 1 and 2, so what is the weight at 1? What is the weight at 1? That is equal to 4, right? And what is the weight associated with the edge, right? So that is minus 3. So 4 minus 3 will be equal to 1. So the weight at 2 is already 1. We will not update it. 0 and 1. So weight at 0 is 0, and weight corresponding to the edge is 4. So 0 plus 4 is 4. What is weight at 1? That is already 4. We will not update it. Now the thing is 5, right? 5 has the weight of minus 1. Minus 1 plus 1, that is 0. So weight at 4 is already 0, right? Weight at 4 is 0, right? And corresponding edge weight is minus 2. So 0 minus 2 is minus 2. So weight at 3 is already minus 2, right? That is also sorted. 4 and 2, 4. So weight at 4 is 0, and the corresponding edge weight is 7. So 0 plus 7, that is 7. So weight at 2 is 1, which is better option, right? So we will not update it, right? Once we find something big, smaller than the current value, then we'll only update it. So weight at 1 is 4. 4 minus 5, that is equal to minus 1. So weight at 5 is also minus 1. So this is the relaxed, right? We have not performed any relaxation over it, and we'll do n minus 1 times just to be sure. This is the case in which only at third relaxation we found out the results, but at some cases at n minus 1 step we'll found some more good results, right? Some more accurate results, more shortest path. Then till n minus 1 iteration we'll be following that, right? And there is a proper reason also. We can discuss it in the later part of the video or in the next video, where we are going to discuss the approach or the code for this particular Bellman Ford algorithm. But yeah, it's just to understand the algorithmic part, right? It is quite simple that at this step we are able to finalize with our result. That is, this is the starting from the source vertex, this is what we are getting the shortest paths, right? So if you see here, for the vertex 1 we have this 4, for the vertex 2 we have this 1, for the vertex 3 we have this -2, for the vertex 4 we have 0, and for the vertex 5 we have this -1. So how can we just verify it? Let us quickly see in this particular graph only. So from 0 to 1 if we go, there is only a single edge with weight 4, so yeah, this is only possibility. From 1 to 2, right, we have only single possibility, so 4 minus 3, 4, this one 4 and -3, that is equal to 1. Yeah, so this is the shortest distance. Now to reach here, right, how many possibilities do we have? We can go like this, we can go like this, right? We can go like this also, or we can go like this also, right? So what is the minimum? So if we go by this method, 4 minus 3 will be equal to 1, 1 plus 4 will be equal to 5. So from this method we are getting a 5. And from this method, right, 4 minus 5, that is equal to -1. -1 plus 1 will be equal to 0, and 0 minus 2 will be equal to -2. So -2 we are going to reach here, right? So this is a good possibility. Similarly, you can see for each and every edge we are going to get the same result. So this is the final solution that we are getting. So this is the full explanation of the Bellman Ford algorithm. If you like the content, then please do hit the like button, and you can also write your comments in the comment section below, or you can follow our channel and follow the Telegram group. The link to the Telegram group is in the description.